Hey folks, welcome to the video. In the last video, we studied the relationship between the index and certain operators. These were compact and finite rank operators. In particular, we saw that adding a compact operator to the identity gives us the index 0. It leaves the index of the identity unchanged. We're going to see that property show up again in this video, particularly looking at the local constancy of the index. Essentially, the idea that the index of an operator is unchanged under addition of compact operators. Let's get into it. We begin with a few facts. The first one here is that B, the Banach algebra of bounded linear operators on a complex Hilbert space that's separable, is also a C-star algebra. This is because T star times T, the magnitude of that is equal to the norm squared of T, where T is an operator, a bounded linear operator on this Hilbert space. Over here, T star is the adjoint of T. That's a concept from linear algebra. So that's the first fact. The second fact is that the space of operators that are compact, the script K, as a subset of B, is a two-sided ideal. These two facts give us that the quotient space B over K is a Banach algebra. B over K is the set of equivalence classes, denoted pi of T for some T that's a bounded linear operator, such that it's the set of these equivalence classes that contain representatives T minus K, where K is a compact operator. Okay, so now that we have these facts can be used to prove the theorem of Atkinson. It's not a theorem that we'll prove here right now, but it is something we will state, and it's a property that we will use. Let's state the first version of Atkinson's theorem. The first version of Atkinson's theorem goes as follows. Let B over K cross be the group of units. These are the elements which are invertible with respect to multiplication in B over K. Let this be the group of units in B over K, and let pi that goes from the group of bounded linear operators B to B over K be the natural projection map. Then the space of Fredholm operators F is equal to pi inverse of the group of units in B over K. A quick remark here is that the set of Fredholm operators is open in B because pi is continuous and B over K cross, the group of units, is open in B over K. The reason for this is because the group of units in any Banach algebra is always open. This is because for every A in the group of units, there's a ball of radius 1 over the norm of A inverse that's contained in the Banach algebra. We may use this version of Atkinson's theorem to formulate a newer version. We'll call it version 2. That says that an operator, T in B, is Fredholm exactly when there is an S in B and K1 and K2 that are compact operators such that ST equals the identity plus K1 and TS equals the identity plus K2. We call such an S a parametrix, or we also call it a quasi-inverse of the operator T. Now the proof for this goes as follows. Suppose T in B is Fredholm, then this is true if and only if T is pi inverse of B over K, is in pi inverse of B over K cross. This is by Atkinson's theorem version 1. Now, T is invertible modulo K over here, and this is true if and only if there exists an S in B and K1 and K2 in K such that ST equals the identity plus K1 and TS equals the identity plus K2. This is by definition of invertibility modulo K, modulo the space of compact operators. An example is the shift plus and the shift minus operators. Now, we encountered the shift plus and shift minus operators back in the introductory video on Fredholm operators. Essentially, the shift plus operator takes a sequence in L2 of Z plus and shifts it one space to the right, places a 0 in the 0th spot, and the shift minus operator takes a sequence and shifts it one place to the left, annihilating the 0th position in the sequence. Now, in this example, the shift minus operator is a parametrics of the shift plus operator, and vice versa. The shift plus operator is also a parametrics of the shift minus operator. We can see this by the symmetry in Atkinson's theorem. The proof for this goes as follows. Let C0, C1, and so on, that sequence be in L2 of Z plus, let it be arbitrary. We know that the shift plus operator takes the sequence and shifts it one spot to the right, placing a 0 in the 0th position, and shift minus annihilates the 0th position, shifting the sequence to the left. So the shift plus operator composed with the shift minus operator on this sequence, C0, C1, and so on, gives us 0, C1, C2, and so on. We can rewrite this as the identity acting on our original sequence plus some operator K1 acting on that original sequence. Over here, K1 is given by an operator from L2 of Z plus to L2 of Z plus, and it's defined by its action on D0, D1, and so on, where it just places a negative sign in front of D0 and annihilates the rest of the elements in the sequence. The composition of shift minus with shift plus gives us something similar, except this time it doesn't change the sequence. So in this case, K2 is 0. So K1 and K2 are compact here. That's because K2 is trivially compact, the 0 map is trivially compact, and K1 maps the unit ball in H here is L2 of Z plus, to a compact subset of the same unit ball in L2 of Z plus. Okay, that means the shift plus and the shift minus operators are both parametrices of each other because they satisfy Atkinson's theorem. Great. Now we can use Atkinson's theorem to further investigate the invariant properties of the index. In particular, we're going to study the invariance of the index under addition by compact operators. Last time we saw that the identity plus a compact operator, that operator's index was 0. It's invariant under addition of compact operators. This time we'll see that for any Fredholm operator, the addition of compact operators gives us an invariant index. It doesn't change the index at all. We begin with a proposition to get to this claim. The proposition is that the parametrics S of an operator, a Fredholm operator, T, is also Fredholm, and in fact it has index negative the index of T. The proof for this notes that the symmetry of Atkinson's theorem gives us that if S is a parametrics of T, then T is also a parametrics of S. That means S is Fredholm by Atkinson's theorem. Now, since ST equals the identity plus K for some compact K, the index of S plus T we know is the index of S composed with T, and that's the index of the identity plus K, which is 0, since k here is compact. We saw this from last time. Thus, the index S is equal to negative index of T. Great. Now we can show that for a Fredholm operator, F in the space of Fredholm operators, a compact operator K in the space of compact operators has the property that the index of F plus K equals the index of F. Okay, let's let S be a parametrix of F such that SF equals the identity plus K1 and Fs equals the identity plus K2 for some compact operators K1 and K2. Then we have that SF plus K equals SF plus SK, and that's the identity plus K1 plus S times K. And similarly, F plus K times S is the identity plus K2 plus KS. Now, since S is also Fredholm and K is a compact operator, SK and KS are also compact. So K1 plus SK and K2 plus KS are compact operators. Thus, S is a parametrix of F plus K2. Okay, therefore, by the proposition above, the one where we showed the parametrix of a Fredholm operator is itself Fredholm with negative index. The index of F plus K is equal to negative index of S, which is equal to the index of F. And that completes the proof. We continue our investigation of the topological properties of Fredholm operators now with an investigation of the homotopy invariance of the index. We already saw that the index of a Fredholm operator is invariant under addition of compact operators. It would be nice if the index were locally invariant. That is, for every Fredholm operator F, there's some neighborhood around it in the space of Fredholm operators, such that the index of all those Fredholm operators within that neighborhood have index equal to that of F. The following theorem states just that. The map index from the space of Fredholm operators to the integers is locally constant with respect to the operator norm topology. We can think of the space of Fredholm operators with index, and each of these operators has index that's an integer. So it makes sense to talk about this map denoted by the word index from F to Z. The proof of this theorem is as follows. We let F be a Fredholm operator with index of F. By Atkinson's theorem, there is a parametrix S that we choose for F, and it's such that S times F equals the identity plus a compact operator, or F times S, and S times F is the identity plus another compact operator. Okay, then we now show that for all operators that are bounded linear with the norm less than that of the inverse of the parametrics norm, F plus D is Fredholm. Inspired by a geometric series argument that we had used in a previous video, we assert that the identity plus ST and the identity plus TS are invertible operators. This is because their norms, the norms of ST and S1 and TS, are less than 1. So the identity plus ST inverse times S times F plus T is equal to the identity plus ST inverse times the identity plus K2 plus ST, and that's given by the identity plus ST inverse times K2. So the identity inverse times S is a left inverse of F plus T modulo the space of compact operators. Similarly, S times the identity plus TS inverse is a right inverse of F plus T modulo the space of compact operators. Also, the index of the identity plus ST inverse plus the identity of S plus the identity of F plus T is the index of the composition of each of these operators. And that's the index of the identity plus this compact operator, and that's 0. Okay, great. Now we notice that since the index of an invertible operator is 0 and the index of S is negative index of F, we have that the index of F plus T equals the index of F. And that completes the proof. Now there's a remark here, and that's that this theorem can be used to show that the index is constant on the connected components of F. We may dive further into the topology of these Fredholm operators by observing the following fact. If we let X be a compact space, we may assign a group to X and a group element to each continuous family of Fredholm operators. We denote this by G, and G is this family parametrized by the space X that maps to the space of Fredholm operators. This group element is invariant under deformations. What does this mean? It means that if there is a continuous family of Fredholm operators, another continuous family, denote this by G prime, it goes from the space X to the space F, that is homotopic to G. Then G prime is assigned to the same group element as G. We say that G and G prime are homotopic if there is a continuous family of Fredholm operators. We denote this family by little g that goes from X across the interval 0, 1 to F, such that G at 0 equals capital G and G at 1 is G prime. Note that if X is the space containing a single point and G and G prime are homotopic, then G and G prime lie in the same path component of the space of Fredholm operators. This idea allows us to investigate the nature of connected components of F.
I hope you all liked that video. In the next one, we're going to be talking about the geometry of bounded operators on a Hilbert space. We're also finally going to look at the topology of the space of Fredholm operators. So stay tuned for that. Like, subscribe. I'll see you all next time.